Now we're going to cover the SN2 from a stereochemistry point of view. So again, I want you to, as soon as you see your alkyl halide, I want you to classify it. You go to the alpha carbon, which is the carbon that has the halide attached to it. And that carbon is attached in this particular case to two other carbons. So this is a secondary alkyl halide. With a secondary alkyl halide, we know we have to be using a strong nucleophile, and we have to also be using the right solvent for the SN2 reaction to go at a decent rate. Alright, so I have the leaving group, which is the halide, the bromide right here. And the halide is to the front. It's coming out of the plane of the paper to the front. That means that when the cyanide approaches the alpha carbon, it's going to have to come from the back of the molecule, from the back of the halide. It's 180 degrees, and that's what we call the back attack, sorry. So when the cyanide approaches the back of the carbon, it's going to form a bond to the back of the carbon, so it's going to be in the back. That hydrogen is going to very conveniently move to the front. It's going to get out of the way. And of course, we're going to substitute the halide so we get the ion in solution. In terms of the stereochemistry, if we were to assign the R and the S to the molecule that we have on the left, bromide is 1, ethyl is 2, the methyl is 3, and the hydrogen, which is number 4, is in the back. So this alpha carbon right here is the S enantiomer of the 2-bromobutane. When we did the substitution, the cyanide came from the back. So when we assign importance, carbon-nitrogen is more important than carbon-carbon. The methyl is still number 3. The hydrogen came to the front, so now we have to be very careful in here. So 1, 2, 3, we are going S, but the hydrogen is in the front. So the stereochemistry of the carbon is the opposite of S. It's R. So when you do an SN2 reaction, we're going to get 100% inversion of configuration. And that's important because, again, we have to actually look at the stereochemistries of these reactions right here. So let's say you have a methyl over here, and you have your leaving group on the other side of this cyclopentane right here, and I have them cis. When we do an SN2 reaction, let's say we use sodium azide. The azide is going to come from the back. It's going to do a back attack, and if it comes from the back, it stays in the back. So I'm going to have inversion of that carbon, but I did not touch the other chiral center in the molecule. That CH3 is still in the front. And if you notice, I went from cis to trans. So that is the stereochemistry of the SN2 reaction. You're going to have 100% inversion of configuration.